Right, so what I'm going to talk about is cooking the books. And so basically the idea is how do we check that, an implementation of the Java memory model is correct, okay? And so, so what's the deal with the Java memory model? I mean, why are we interested in this in 2015 anyway? So in 1999, or 1998, 99, Bill Pugh came up with a paper that is called The Java Memory Model is Fatally Flawed. Okay, so the basic idea there was that there are a bunch of compiler optimizations that are required for Java to be reasonably performant that were not allowed by the specification of threads and synchronization in Java. So they set up to, improve it, change it, fix the wrong things. And so 5 years later, they came up with the current specification of the Java memory model. And so they fixed a whole bunch of things, and that's very good. And many of the optimizations that weren't allowed before could be shown to be allowed. So that's also good. And it had some interesting properties, like, for example, the data race freedom guarantee that says that if your program has no data races, you will only have sequential consistent semantics was proved. So that's cool. Unfortunately, a couple of years later, David Aspinall and Jaroslav Sepsik came up with a paper saying, okay, so here's the Java memory model. I'll show you a few examples. Some are good, some are bad, and some are ugly, okay? And so what this is showing is that, the formalism that they use to define this memory model is at times very complicated, and it leads to some very subtle errors. And this was made even worse in their second paper in this topic, which talks about the validity of certain program transformations that were supposed to be allowed, but it can be shown by a few examples that in these examples they're not allowed, and there are other things that are not supposed to happen that do happen, right? So this is the current state of affairs in the Java memory model universe. So actually, there are ongoing efforts in trying to improve this state. So, but why is this so hard? What's the problem with the Java memory model? So, the goal of the Java memory model is to define all possible behaviors of a concurrent Java program. And in doing so, you cannot just say, okay, we're just going to have sequential consistency. Whatever architecture you have to implement sequential consistency, because that's extremely expensive. Most concurrent architectures have relaxed memory models that allow reordering of instructions. And while this is not visible in sequential programs, this is very, very visible in concurrent programs. So if you want to implement sequential consistency in an x86 machine, for example, you have to put a fence in between every write and every load that follows. So that'd be terrible, right? And so the same thing applies to Power and ARM and so on. So here's the state of affairs. We have a very complicated formalism, the current definition of the Java memory model. We have different architectures that do all kinds of reorderings or relax the behavior of the memory for concurrent programs. And on top of that, we have compiler optimizations which reorder code massively and could lead to unexpected behaviors if what you expect is sequential consistency. So the question is, if you do have to implement the Java memory model, how do you do this, right? It feels like this. It's like walking on a tight rope, but there are many ropes, and they go in many directions, and you have no idea, like you have this spec at a very high level, then you have the spec of the machine somewhere there, and you have a load and a volatile write, do I need to put a barrier? Do I not need to put a barrier? Do I need to put this one or that one? It's really hard. Okay, so because this is really hard, we want to know how can you get it right? How can you do this correctly? So the basic idea is that we're trying to prove that for a certain program P, the behaviors allowed by the JMM are strictly larger than the behaviors that are allowed for the program in x86 or in Power or after running a bunch of optimizations on top of the program. So we want to see that doesn't happen is this, that your program, when run on an x86 machine, will go beyond the allowed behaviors of the JMM. Okay? So let's look at why this is hard. And I'm not going to show you the formalism because it's messy, but I'll give you a few examples. So let's say you're a reasonable programmer and you expect, for the most part, sequential consistency, and you get this program. So this is a very simple program. You have a single variable x, which is initially 0. And then you have 3 writing threads, which protect the writes with locks. So you know that these are atomic writes. And so you have a 4th thread, whose only thing is to print this variable. So it continues reading the variable and printing it. Right? So you know that the writes are going to be sequentialized somehow because there are locks to enforce that. Right? So you expect to get a bunch of zeros and then a bunch of ones, and maybe some twos, and then from then on 3s. Right? So that's what you expect. In Java, in the current state of Java, you can get any random sequence of 0s and 3s. Okay? In between 0 and 3. So it's just, acceptable according to the Java memory model, but, we speculate that no reasonable machine would do that. Virtual machine architecture, yes?
Yeah, I'm asking a question. Do you know of a virtual machine that will actually do that?
No, I hope there aren't, but that's where we're going, right? I mean, we're trying to see what the actual machines do, Okay, so here's another example. This one is actually correct. So this is typically known as the either publication idiom or producer-consumer example. So we have 2 variables, a flag, initially 0, and a data variable. And so the idea is that on the left-hand side, we have a thread that produces some data. In this case, it's very silly, 1. And then it publishes with the flag the fact that data has been produced, and then the right thread is waiting for the flag to become 1, and then it uses the data. So everything is fine here because I've made flag volatile. Okay, so that's the idea of volatile. It means that if I make a write on a volatile, and then on the other side I've made a load on the value written by this other thread, I'm guaranteed to see everything this thread has done before that. If, on the other hand, I remove the volatile there, I can read any value for data, or 0, 1. Okay, so another more sophisticated example is what is usually called the independent readers, independent writers example, IRIW. And so what we have here is 4 threads. We have 2 variables, global, x and y. They're initially 0. And then the writing threads write one to x, the other to y. And then the reading threads read one first x and then y, and then the other first y and then x. Okay. And so it turns out that if according to the Java memory model, it could be to happen that one thread reads x becoming 1 before y has become 1, because you see y equals 0 in the second read, whereas the other one sees the opposite thing happening. There are many ways in which you could explain this. For example, if reads can be reordered, this is totally normal, right? If you reorder any of the reads in any of the threads, then that's possible. The question is, for volatiles, this shouldn't happen for sure. Okay, so this is an explanation of what I've just said. So you could consider, a possible interleavings of this, and you can see that this behavior is only possible if you reorder something somehow. All right, so because this is all so complex and so messy, Doug Lee, which is a brilliant guy, decided that if we want to help our virtual machine writers, so he created this website that is called the JSR 133. That's the Java memory model. Cookbook for compiler writers. Okay, and this is great. This is basically a document that tells you if you're implementing the JMM on this architecture, this is what you have to do, and if you're implementing it on this other architecture, this is what you do. So importantly, he wrote this about 10 years ago, more than 10 years ago. So it's only natural that there are a few errors, because back then we didn't even know what the formal semantics of a power machine were, for example. So the basic idea of the cookbook is that it gives you a bunch of tables, in particular, a sequence of tables that say for each 2 operations. So for example, here I'm looking at the first row, first column. It says, okay, so if you have a normal load followed by a normal load, the Java memory model allows these 2 things to be reordered. So you don't need to do anything in any architecture, whether it reorders them or not. But for example, if you have a volatile load followed by a normal load, then you should not reorder this in any architecture. Okay? So if your architecture potentially could reorder your implementation of a volatile load and a subsequent load, then you should prevent this somehow. Okay? And so on for all other instructions. So how do we go about doing this? Because we don't want to give specific rules in forms of this table for each architecture, he designed an intermediate representation where you have sort of generic barriers that will prevent the reordering of things. So for example, say here it's saying that if you have a volatile load followed by a normal load, then you have to put a load barrier. Okay, and then if you have a volatile load followed by a normal store, then you have to put a load store barrier. And then the next table tells you what load means for x86, what load means for power, what load means for ARM. Okay, so that's the idea. So you first table tells you what is possible and what is not possible in Java. The second table tells you generically how to implement this. And then the third table tells you specifically for your architecture, here's how you implement each of these things. Okay, so I'm going to focus now on TSO x86, which are the same architecture, and power, which are some reasonable architectures. And so what I will try to do this here in this work is to show that all the behaviors that you can get in Power x86, if you follow the Cookbook rules, are included in an intermediate semantics that I call the Cookbook low, which has actual fences and caches and all these low-level instructions. And this is in particular included in what I call the Cookbook high, which is a very strong flavor of an implementation of Java. And so Cookbook high, for example, has volatiles and logs and things like that. And then the Cookbook high is definitely included in Java. So if you take the inclusion from bottom up, you get something that is Java compliant. That's what we're going to show. So if you follow the rules, you get Java compliance. I've said this. And so in particular, we have chosen to follow the power route. So basically, we're going to propagate the power semantics to normal variables all the way up to Cookbook high. The reason is because power is a weaker semantics than x86. So if you propagated semantics of power, you're only allowing more things than x86 actually does. So that means that you're okay. And for volatiles and log, obviously, we're going to give sequential consistent semantics. That's what they're meant to do. Okay, so it'd be really nice if we could, when I started, I thought to myself, okay, so all I need to do is to say which things can and cannot be reordered, and then I'm done. It turns out that that's not enough. So here's an example. This example is a little bit convoluted, so try to follow. So we have two objects, O and O prime, who are of the same type, so they have a field F, and they're initially 0, okay? And so we have a left thread that just writes O prime in the field F of O. And then we have an intermediate thread, the thread in the middle, that reads O.F. If we follow this trace, it's going to be O prime in general. And then on the F field of O prime, it will write O. And then the rightmost thread reads the F field of O prime, and to whatever it read, reads the field F again a second time. And so the question is, can we ever possibly get the behavior that R0 lands on O, the object O, meaning that O.F on the left-hand side got O prime, then O prime.F got O, and then R0 finally gets O. But when we read O.F by doing R0.F, we get null, which is the initial value of O prime, of O, sorry. So is this possible at all? It turns out that it is. In Power, this can happen. This is usually called the write-read causality test. And the reason, well, there are many reasons why this could happen, but if you want to think about it operationally, think about writes being propagated to different threads at different times. So the fact that a thread could read a write doesn't mean that all threads are going to be able to read this write at this very moment. So for example, the write of O.F equals O prime was propagated to the second thread, but not the third one. Whereas the write of O prime.F was propagated to the third one, maybe or maybe not to the first one. Okay? So this complicates everything because this means that we can no longer think about reorderings alone. Now we need to think about how writes are propagated to different threads. And also notice that in this example, there is no synchronization whatsoever. So I'm not talking about volatiles, no logs. Whatever I need to do this applies to all normal variables of Java. So when faced with this, we have two options. If we want to have the stronger semantics, which we can reason about only by means of reorderings, we can just say, okay, we'll disallow this thing. Forget about it. I'm just going to compile something that doesn't allow this kind of problem. But then that would mean that for all loads, I would have to put a fence after. I would have to put a barrier. But these are normal loads, right? So this is a little bit too much to us. That means that all loads, which is the most common memory operation in Java, would have to be followed by a barrier, very slow operation. the other alternative is to propagate the behavior to Cookbook high, which is what we do. Okay. All right, so now I'm going to show you a little bit of the semantic framework. So the idea here is that I use a uniform semantic framework to encode all the semantics and to carry out the proofs. So the semantic framework is as follows. So we have threads that contribute code to what I call the temporary store, or you can think of this as a pipe where you put operations. And then only when things get out of the pipe, they're propagated into memory, okay? So basically think that all threads are putting things in this pipe, but they're not performed until they get out of the pipe in the memory. So I'll give you an example. So here we have 3 threads. And I'm going to start by the middle thread by executing the variable c gets false. Okay, so ff is false. So when I do that, I just add a write of the variable c with value false by thread T1, and then I move on to the next thread. So now we have a write of variable x with value false, and so on and so forth. Now for writes it's easy, right, because you have the value, but for reads it's a little bit more complicated. Now you have to delay this read operation, but the thread needs a value to continue. So what we're going to do is just have placeholder values, right, just like what you would do if you're implementing futures or something like that. So instead of reading directly, we create a placeholder value, in this case it's new, and then we move on with the execution. So threads contribute things into the pipeline, and eventually you have to empty the pipeline. So to do that, we have another set of rules that tell you when an action that is in the pipeline is allowed to get out. And changing the definition of when an action is allowed to get out of the pipeline, you can encode different memory models. So for example, if you want to encode TSO, whose only relaxation is that a write followed by a load can be reordered, you say, okay, so if I have a write by a thread and a load by the same thread, then I can execute the load directly. I don't need to wait. And so the idea is that one. You just encode when things can be reordered, and then you perform. So for example, here I'm going to perform the read, which is in the 4th place. So I say, okay, so this is a read by thread T0. There's only one write of thread T0 before it, and it's on a different variable. So the read is on Y, the write is on X. So I can just reorder it, and then I can actually perform the read, and that's it, I'm done. So that's a general framework. I'm not going to talk much more about the framework. So how do we deal with this store atomicity relaxation, the fact that writes can be propagated to different threads at different time? Well, the basic idea is simple. In this pipeline, each write has a set of threads that can see it immediately. And if you're doing a read on a write that has been propagated to this thread, so for example, the first read is in the set of the write, then this read can see this value. But the second read, which is by thread T0, which is not in the set, cannot read this value. So this way you encode atomicity relaxations. And so the rules are, I'm just going to show you 2 rules, and this is the end of the formal stuff. The rules specify how writes can be propagated into memory. So the first rule just says, if you can find a write in your, so this sigma 0, sigma 1 thing is this temporary store. If you can find a write such that this write does not conflict with anything in the front part, that's sigma 0 there, then you just update it into the memory in the store S. And the second rule says, at any point you can choose to increment the set of threads that can read this write immediately without being performed in the main memory. Okay, so that's the basic idea. All right, so now let me talk a little bit about power barriers, because this is important for what follows. So power barriers come in 2 flavors, a lightweight and a heavyweight barrier. So the heavyweight barrier enforces ordering between all operations. So if you put a sync, anything that came before or after it by the same thread is guaranteed to be preserved in that order. But moreover, it guarantees some sort of consensus. That meaning that if you have an operation that was aware of some actions that happened before it, and then you have a barrier, and then you have another operation, then the operation that follows the barrier also has to be aware of all the things that were visible to this guy. This is called cumulativity in the power documents. And the lightweight sync, however, first of all, doesn't prevent all kinds of reorderings. It allows reorderings of writes followed by read, which is the normal relaxation of TSO. And it does not enforce this kind of consensus. And so this is shown in the example below, which is basically the IR-IW example repeated, except that I've added LW sinks in between the reads. And so it turns out that although there is no write read, which can be reordered, this behavior is allowed in Power as is, okay? So you can perhaps see the problem now because it's marked. The thing is that the recommendation for, of the cookbook for implementing volatile loads imposes a load load barrier. But if you look at this column, the load load barrier only implements an LW sink, a lightweight sink. Okay, so which means that the example that I just showed you can actually happen. And so that's a bug. Okay, so that's what I just said. If you run this example where everything is volatile, you can have a weak behavior, and this is exactly what volatiles are supposed to avoid. So the fix is easy. You just change the lightweight sink for load load into a heavyweight sink. So we ran this on machines, and we actually saw it happening. So we ran it on a 32-core Power 7 machine, and we tried different virtual machines. We tried JAIX and an IBM machine, and it happened. I was surprised. I didn't expect it to happen, actually. We also found other bugs in implementations of volatiles in Fiji in ahead-of-time compiler. And so we also asked around to see, do people go by the formal definition of the JMM, or do they go by the Cookbook? And it turns out that we got a fair amount of people saying that they go by the Cookbook alone. They just don't want to read this other thing, which is messy. So in terms of results, guarantees that we provide, okay, so I'm just going to state the lemmas, but basically you can follow the picture on the right-hand side. So one says that every TSO behavior that is x86 is included in any behavior of Cookbook Low if you follow the recipes. Same thing for Power. If you follow the recipes from Cookbook High to Cookbook Low, then every behavior of Cookbook Low is embedded into behavior of Cookbook High. And finally, ultimately, the semantics of Cookbook High is sufficiently strong that is guaranteed to be included in the semantics of the Java memory model as is, the formal definition of the Java memory model. So that concludes my talk. A disclaimer is this is not a proposal for a new JMM. We're not saying you should use Cookbook High as your new strong JMM. What we're saying is if you follow the recipes, you get something really close to our Cookbook High formal semantics, and this is guaranteed to be a correct, a faithful implementation of the JMM. So if you were to take the stronger semantics where you disallow the store atomicity relaxations, which complicate everything, you would have to instrument every single load of normal variables, and that should probably be very, very expensive in terms of performance. And so we, in terms of future work, we'll look at how do we incorporate program optimizations, program reorderings into our Cookbook High framework. So that means that we have to relax it to allow more behaviors to be exposed. And that's it. Thank you.
Just a quick clarification. In your talk, you pointed out a problem with the cookbook, and you gave a fix.
Yeah.
And then you also proved 4 lemmas, and I assume that's after you've done the fix.
Yeah, it's a fixed version, of course, yeah.
Have you looked at ARM yet, or is that on your list?
So actually, we're arguing about ARM by means of Power because we had the idea that ARM and Power were very similar. But Jad recently had a paper where she shows that there are things that happen in ARM that do not happen in Power, and so I didn't even try to get the formalism of ARM in place. So. What's that? Yeah. I mean, I don't make arguments about ARM.
Just one of the things there, the x86 hardware is very conservative.
And that makes like adherence to the Java memory model much easier, sort of almost can't fail. You have to do a few things and they're obvious.
Yeah.
But I think that's not true of ARM. I think there's going to be a lot more work the compiler writers will have to do to get ARM correct. So I'll be very interested to see how well the cookbook survives, you know, intense study on the ARM.
So I think the cookbook is somewhat conservative for ARM as well, so it puts DMBs all over the place, basically, which should be fine. The reason why I didn't include it in this paper is because I did not have a quite good understanding of what the formal definition of ARM is at the moment. So I couldn't, embed it in my operational framework to be able to carry out the proofs. So, but I think it should. I mean, I think the cookbook should be fine. It's a very conservative document, by the way.
Thank you.
Yeah, thank you.